This video here contains a very brief introduction to getting started using the Schrödinger program suite. So I'll begin by powering Maestro. Maestro is the graphical interface that is used in the Schrödinger suite. As the first thing, what I do is that I click all the different icons up here because it gives me a lot of opportunities for building and manipulating structures in a more easy way here. So we start here by building a small molecule that could, let's take this one here. Now we can add a hydroxy group to this point up here, for example, and I can now take the structure like this here. Now what I can do is that I can choose different representations. By double clicking here I get another representation. I get a representation here, which probably is something that most of you are more familiar with, and then I get here a space filling representation like this, which now shows how this molecule here occupies part of space. Now the only thing that I will show in this short video here is how to set up calculations of the type that we are going to use in this course here, namely calculations that are based on molecular mechanics. So we do this under applications, and under applications we have two possibilities. We can either have the applications in what is called a task view, then it is called tasks up here. I like to have it in the view that is called application view. So if it is not set to application view in the default settings on your computer, you can shift it into the application view. Now by having this in the application view here, we have now access to the various programs here that make up the Schrödinger suite. So in our course we will be most interested in using the macro model program here, which is a molecular mechanical based method of calculating energies and structures of the molecules. So what we can do here, for example, for the molecule that we have built, is to choose a minimization, meaning that we will now minimize the energy with respect to the position of the nuclei. Maybe before we do this, we need to go up under workspace and create a project entry. We can call it for test. So it comes like this, and you can now see out here that the calculations that we do, they will now be referred to under the label test. So if we now take the application view again, we can do the macro model, and then we can do the minimization. What we need to think about here is which force field we will choose. Here we can choose different force field. We will just choose the default one, OPLS 2005. If we have solvent, in our case here we don't have any solvent. And then we need to choose on some cutoff values for the force field. We usually will just use the default ones, 7.0 for the van der Waals, 12.0 for the electrostatics, and for the hydrogen bonds this is 4.0 if these are modeled explicitly in the force field, that is. Under constraints we have a possibility for constraining some atoms to specific positions or some bonds to specific lengths, but here we will make a completely unconstrained minimization. We can do some substructure manipulations, and under minimization we can choose which method we will use for the minimization. If this is a pre-conjugated gradient based method, and there's also a Newton-Raphson method here, which is a second order optimization method. So usually we will simply again choose the default one, the maximum number of iterations, and then the convergence threshold here. So the maximum number of iterations, in some cases this needs to be increased to a bigger number. So if we start the the calculation here, then this is a very fast calculation, so it should only take a few seconds. You can see here that this one turned green now, meaning that the calculation is running, and it's already done now here. So viewing the output from the calculation, we have two possibilities. We can either go up here and click the table, and in this then this table will open here, and this contains kind of a summary of the most important findings from the calculation. So we can see, for example, here that our calculation is named test, and that the predicted energy is 27.733 kilojoule per mole, I think. Usually we need to get some more information, so we need to go to the job list here, to click monitor, and then we can click on the calculation that we have done. We can, under details here, take the log file, and this log file here now contains much more information than just the very final output from the calculation. So going through it very briefly here says that it tells us the number of parameters that we have in our force field, and then it tells us here that the total energy for the starting conformation of the molecule, this is 41.41, and then it begins to do the minimization. You can see here that what happens when we do the minimization is that the gradient here go down in value until it comes under the threshold of 0.5, and also that the energy here decreases from the 41.41 kilojoule per mole and then down to this 27.73 kilojoule per mole, which is the final predicted energy here. So from this is a very simple calculation, but usually we can get a lot of valuable information from looking at the output file here. We can also go back here to the original molecule here, and then by clicking either the shift or the apple on bottom here on the computer, then we can mark both of these entries as done here, and we now get, you can see, an overlay of the two structures, so we can see what actually happened to the molecule when we did the minimization. Okay, so this was just like this, a very brief introduction. You have more opportunities over here for manipulating the structures, shifting elements from being, for example, a carbon into some other elements. We can take hydrogen into a fluoride like this. We can make a single bond into a double bond like this. We can do it the other way here. We can increase the charge, we can decrease the charge, and so on. So in the exercises, you will do more on such kind of calculations here. We will, in addition to simple minimization, also search for different possible conformations of molecules and decide which conformation is the most stable conformation of a given molecule, that is, which conformation possesses the lowest energy. And you will also be trained a bit more in how to manipulate the structures by using the entries over here.